Okay, let's move ahead with this. Welcome to the session. Hopefully, there won't be any glitches and things will go on smoothly. If you go to 360 Digit MG website, you have an option called Mind Map. When you click on this option called Mind Map, and when you do a drop down, you will find an option called AI and Deep Learning. When you click on that, you will see a specific mind map. And this mind map can be used as a reference for you all to learn neural networks. Here in Deep Learning Primer, we understood about human brain in the previous modules. And we understand that neuron is a basic unit of information. And there is also another thing called as 100-step rule, which says that any repetitive task, when you start working on that, it will not cross 100 neurons. You will never exceed using more than 100 neurons. You'll use up to 100 neurons. However complicated the task might be, if you do it repetitively, then only 100 neurons is what you end up using. But typically, human brain has millions of neurons. This is what we have understood. Then we spoke about compositionality. What do you mean by compositionality? Compositionality means human brain as well as your neural network would have something called as hidden layers. And it is going to learn small things, very basic things first. Then it will move on to understand slightly complicated things. And finally, it will understand very complicated things. So initial hidden layers in the neural network, you'll have what input layer, and you have bunch of hidden layers. Okay, you have hidden layers. The first hidden layer is initial set of hidden layers or initial set of hidden layers capture low-level features. If it is image, then it captures edges, pixel values, etc. Then the next set of hidden layers capture mid-level features. It captures mid-level features. Mid-level features means parts of the human face like eye, nose, mouth, ear, etc. Then you have final set of hidden layers. Final set of hidden layers include or captures high-level details, such as the entire human face if it is a face recognition model. Then after extracting all the features, automatically your deep learning models extract all the features. Once they extract all the features, you'll have an output layer which will give you the predictions, which will actually give you the predicted values. Output layer, input layer. And in each of these layers, we also understood that there will be something called as neurons. Number of neurons you want to have in the hidden layer is a hyperparameter. You need to decide how many neurons you want to have in each of the hidden layers. How many neurons or how many hidden layers you want also is something that is decided by you. So number of hidden layers and number of neurons within each hidden layer is a hyperparameter. That is, you keep changing and you keep experimenting and then determine what or how many hidden layers is actually giving you the right result. And how many neurons within each of the hidden layer is actually giving you the right result is something that you need to figure out. The number of neurons in the input layer, depends on number of inputs that we have in a database. In the data set or data frame, if you have 5 neurons or 5 inputs rather, if you have 5 inputs, then you will have 5 neurons in the input layer. Number of neurons in the output layer depends. Number of inputs in the input layer will be 5 because you have 5 inputs plus 1 bias. So there will be total 6 neurons in the input layer. 5 inputs, so 5 neurons plus 1 neuron called as bias. Then you have in the output layer, the number of neurons that you should ideally have, it depends on what is your output variable. If the output variable is continuous, then you will have a single neuron in your output layer. Then you have in your output layer, you're going to have a single neuron, one neuron. If your output variable is discrete, categorical, in 2 categories, then also you would have a single neuron. Sometimes people also have 2 neurons, but say assume that you have single neuron. And if your output variable is discrete with say more than 2 categories, and example is say 10 categories, then in the final layer you're going to have 10 neurons. If you have 10 categories as an example, then you'll have 10 neurons. If you have n categories, whatever be the 10, 3, 4, 5, 6, whatever be the count, then you'll have n neurons. So the number of neurons in the input layer depends on number of inputs that you have in your data set. Plus there will be one additional neuron which is called as bias. And in the hidden layer, or in the hidden layers rather, you can have one hidden layer or multiple hidden layers. How many hidden layers do you want to have? That really depends on you as a data scientist. You need to experiment. Number of neurons is also left up to you, it's a hyperparameter. But number of neurons in the output layer depends on what is your output variable. Okay, next. That's it. Slowly and steadily, we will be building on top of this. And we also have discussed that every neuron will have 2 components. Will have 2 components. One is your integration component. Integration can be summation like this, quadratic function or spherical function, which we have discussed previously. Quadratic and spherical. Or you can have some other integration function, but usually summation is used. You can safely use summation, no issues. Then the next component is called as activation component or activation function or transfer function. Here, this component will have activation function or transfer function. There are a bunch of activation functions, and we are going to talk about those today in this module. Okay. And we also have deep learning libraries. A few of those are given here. You have TensorFlow from Google, which is a low-level programming language. And within TensorFlow 2.0, 2.x, 2.1, 2.2, 2.3, 2.4, whatever, officially they recommend Keras. And Keras was built by a person called as Francois Chollet, which is a high-level programming language. That means even a business user will be able to easily understand and write the code. And we have PyTorch, the new kid, a new kid in the street. You can think in that way, new kid among the deep learning libraries. But PyTorch has actually overtaken the demand of Keras or TensorFlow. TensorFlow, you need to write a lot of lines of code. PyTorch, the beauty is that it works exceptionally well when you work in a distributed environment. When you have 10 GB, 20 GB data, and say each of your computer has only 2 GB, and if you have 10 GB data, each of your computers have only 10 GB, then how would you store it? 2 GB in one hub, one computer, 2 GB in another computer, 2 GB. In that way, you split. Okay. So, because each of your computers have 2 GB, this is what happens. Okay. So, 2 GB, 2 GB, 2 GB, 2 GB. Now, if you have data in multiple computers, the data is distributed. It's not in single computer. It is distributed among all the available computers or servers. And if you want to work or build a model by accessing data from all these different computers and still do a good job, then PyTorch works exceptionally well in comparison to TensorFlow. That is the reason why this has caught the attention of the world. We have something else called as PyTorch Lightning. And I'm going to take a session on PyTorch Lightning at a later point of time, but then yeah. And we have MXNet from Amazon. You have Caffe, which is quite old. Theano is the first deep learning library which was introduced to the world. But then not many people are pursuing Theano or Caffe, so it's not being developed beyond a point. CNTK is a deep learning library from Microsoft. I think that is all that we have spoken about. Now we need to switch gears and move into the next discussion. We already have discussed about Perceptron algorithm. And Perceptron algorithm can handle linear patterns, linear boundaries. And then you have multi-layered perceptron, which can handle non-linear patterns. So you have linear patterns and you have non-linear patterns. Linear patterns are handled by perceptron, non-linear patterns are handled by ML, multi-layered perceptron. Okay, next. As we have discussed, if you have input, you supply that input to the neural network, which has a layer. It will extract different patterns from the data, the first set of layers. Then it goes as an input to the next layer. That would again supply inputs to the next layer. Again, it will supply inputs to the next layer, and then you get output. Again, those outputs go into the next layer, and finally, you get the output. So here, if you have an image 4, it will traverse through all these layers. These are all hidden layers, hidden layer 1, hidden layer 2, hidden layer 3, and hidden layer 4. Finally, you have an output layer. That output layer will tell you on what this number is. It's telling that this number is 4. That's how it traverses. And one more very important thing is when it comes to perceptron algorithm, we will have within perceptron, you just have one neuron in the output layer, and all these will get connected to this, and you have no hidden layers. Okay, friends, you will have no hidden layers, and there will be only one single output layer. This is how the perceptron algorithm works. But when it comes to multi-layered perceptron, you'll have hidden layers. Say this is your input layer with 5 neurons. Then maybe you have one hidden layer with 3, another with 3, another with 2, and finally the output layer. If every neuron is connected to every other neuron, let me establish connections in that way. This also should be connected to these 3. This also should be connected to these 1, 3, 2. So, if every neuron is connected to every other neuron, when you move ahead, if every neuron is connected to every other neuron, then it is called as multi-layered perceptron or artificial neural network or fully connected network, fully we call it as epsilon, or it is also called as dense network. Okay, it is also called as dense. Multi-layered perceptron or artificial neural network or fully connected network or dense network all mean the same. So on one side you have perceptron algorithm, which doesn't have any hidden layers and one single output. On another side you have multi-layered perceptron or artificial neural network or fully connected network or dense network. All that means is that you will have hidden layers and every neuron will be connected to every other neuron in the entire network. That is why it is also called as dense. Dense means there are too many connections, right? Dense. Okay. And one more very important thing that you all have to remember is that except for the input layer, every other neuron in every other layer will have two components: integration, activation, integration, activation, integration, activation. In that way, every neuron except for the input layer neurons, all the other neurons will have both the integration and activation components. Only this layer will not have integration and activation. Okay, so input layer does not have integration and activation components. Except for this, all the other neurons will have both integration and activation components. Friends, one more thing, very, very important thing. Usually what happens is, when we are listening to a theory lecture, which is as dry as neural networks, then you tend to sleep. Okay, or you will feel sleepy at least. To avoid that, I request you to make a running notes. As and how you're watching this, take a book and a pen, keep writing. Whatever you can understand, keep writing that. And typically what happens is when you listen to this for the first time, you might be able to understand maybe only 40%. So you'll understand only 40% of what is being discussed. If you watch it once again, your understanding will increase to maybe 60%. And finally, if you further understand, you might reach 80%. So at least listen for one time, watch the video another 2 times, and you should be able to cross 80%. And this is what is needed for you to clear the interviews. Okay, so let's move forward. So now we will spend some time on activation functions. What are these activation functions and why are they in the first place needed? So first, there are a few activation functions. Let me talk about these, then I'll probably do a deep dive. You have something called as identity function. That means if you have a neuron like this, let me draw it. In this, you'll have integration component and activation component, right? And finally, you will get an output. And you'll have inputs x1, x2, x3, and you'll also have one bias, which will always have 1. And you'll have weights B, W1, W2, W3. This B bias is also a weight. Okay, that is also a weight. Now, what happens is you do B multiply B into 1B plus W1 x1 plus W2 x2 plus W3 x3. And once you do this, you get some number. That number is passed to activation function. An activation function will do some operation, some math operation, and then give you the output. If you use something called as linear function or identity function, if you use linear function or identity function, then what will happen is whatever integration component you have, you pass on the same thing to activation component, and finally you get the same thing as output. That means if you apply linear function or identity function, there is nothing that you do. You just take whatever is the integration component and pass this as is to the activation component. There is no change. Then you have something called a step function. Already we have discussed about step function and what it does. So if you get the integration component, that is this component, and if you get a value which is greater than or equal to 0, if you get a number which is greater than or equal to 0, output will be 1. If you get a value which is less than 0, output will be 0. And that's how it works basically. This is called a step function. It appears as if it's a step if you climb steps. Then you have something called as ramp function. Within ramp function, what happens is, if the value is greater than 1, if you get the integration component value greater than 1, then the output will be 1. Or if you get that integration component value, which is in between 0 and 1, say you get a value as 0.6, then what will happen is output will also be 0.6. It will be exactly that function value. If this integration value is less than 1, less than 0, then the output will be 0. This is called as what function? Ramp function. The disadvantage with both of these functions is that you cannot find the derivative or differentiation at these points. Wherever you see that sharp bend, you cannot find the differentiations. What do you mean by differentiation? Gradient. What do you mean by gradient? Rate of change. So let me do one thing. Let me quickly spend some time and explain you all what that means. And let me take a black screen. Differentiation. Differentiation is also called as gradient rate of change or slope. All mean the same. In neural network, what did we talk about? That there will be something called as an error surface. And if your weights are randomly assigned, initialized somewhere here, then you know what the output is. Loss. Loss is somewhere here. Good. Then what do? You actually update the weights and look at what is your loss value. Again, update the weights, check what is your loss value. Keep continuing this process, friends. Keep continuing this process of changing the weights and then minimizing your loss. So from this point, you reach this point when you change weight from this point to this point. So from A to B, when you change your weights, the loss value has changed from L1 to L2. This is called as the rate of change. If I change the weight from A to B, what is the rate at which loss is getting minimized? This is also called as slope. It's coming down. And this is also called as gradient. Gradient or rate of change or slope or differentiation, derivatives all mean the same. Okay, so hope I'm putting some light into what else has to be talked about here. So here, when it comes to the derivative, typically, whenever you have these sharp bends, if it's a curve like that, sharp bend, then the derivatives cannot be identified because of certain reasons, which is beyond the scope of this discussion. Sorry. Okay. That is the reason why sigmoid functions became famous, because you don't have that sharp cusp or sharp bend. You have a smooth finish. This is called as sigmoid function. Okay, and here is a formula for that. So in sigmoid family, we also have something else which is called as tanh, which is hyperbolic tangent. This is hyperbolic tangent. And then we also have something called as Rayleigh. The abbreviation of this is rectified linear unit. Then you have other things such as leaky Rayleigh. Then you have something called as max out. Okay, then you have something called as ELU, exponential linear unit. Exponential linear unit. All these things we will spend some more time and understand even better. Even before that. This is a typical neural network algorithm. When you use the integration function as summation, what does it do? Additions. But with the weights you are multiplying, right? If you have x1 here and w1 here, w1 into x1, you are multiplying. And then if you have W2 here, W2 into X1, then you add, right? W3 X1, then you add summation. Right? So it is multiplication and summation functions which are going on. When you do multiplications and summations, what will happen is your so-called network is going to collapse like this. It will collapse and ultimately it will stop. Meaning what? If you have an error surface like this, okay, and if your weights were randomly assigned here, then the corresponding loss will be somewhere here. Corresponding loss will be here. But if you're going to use linear functions, linear activation functions, then since the neural network only uses multiplications and additions, your network will kind of collapse. Hence, when it comes to activation functions, we need to use non-linear functions. The moment you have a non-linear step, your network will not collapse. So what will happen is network collapsing means it will again get updated, and then since your network has collapsed, it has reached a single point, your algorithm will not learn any further. It will stop there. But ideally, you had a chance to come down here. You had an opportunity to come until here. But that's not happening, right? I mean, that will not happen if you use linear function. Hence, people use activation functions, which are non-linear in format. Now, what I'll do is, I'm going to spend some additional time in helping you all understand about all the various activation functions that exist. But also remember that activation function has another name. Do you all remember what name it is? Anyone who remembers what is another name for activation function? Transfer function. Activation function is also called as transfer function. Because what happens is, it has say both integration and activation. Activation function will take whatever input it gets and it will transfer that to the output. Okay, it will transfer that to output. And we have already spoken about identity function. Identity function is also called as linear function, or it is also called as linear curve. Then here you have another activation function which is called a state step function. So on this, you'll have your output, and on this, you'll have your input. For example, if the input values, or if the rather activation function values are in between 0 to 0.5, then the output will be 0. Output will be 0.2. If the activation function values range from 0.2 to 0.4, then the output value will be 0.4 if the activation function values range between this point to this point, so on and so forth. Okay, so now that you have straight lines like this. Can I call this as a linear function? Yes or no? Can I call this as a linear function? Or do I need to call it using some other name? Is it linear or non-linear, friends? Come on. You need to think through an answer. It is non-linear because is it forming a straight line? No, these are all independently linear straight lines. However, this is not called as linear. Linear means it has to be a straight line, simple. This is not a straight line, it is like this. So this is not considered to be a linear function. This is considered to be what? Non-linear. Okay. Now, activation functions are usually referred to as the non-linearity functions, usually. Then you have something called as state step function. Okay, one more thing, quickly let me help you understand. You have a solid circle, a filled circle. Filled circle says that at that point, the output value there is valid. So that means if you have the function value as 0, output will be 0. But then if you have a specific circle which is open circle here. This means that output variable is not valid. Output is not valid at that point. So if your output is 0.2, output won't be 0. Output will be that is what you have to remember. Just a few things for answer. Then you have step function, which is used extensively in Perceptron. Here, you need to define a threshold value. Okay. So, if you look at this, there are two things, right? In one, you're saying that whatever be your threshold value, if you get exactly the threshold value, whatever value you would have given, then the output will be this. If it is less than or equal to the threshold value, I mean, in a neuron, you'll have two components, integration, activation. If the activation is step function, whatever value you get here, that will go here. Say you got a value as 0.8. And say you had a threshold of whatever. I mean, say 0.8 is itself is your threshold. If it's 0.8, then you'll get an output which is maybe 1 or 0.5. And here maybe it is minus 0.5. If it is exactly 0.8, then it doesn't fall here, it will fall there. Okay, that is the notation for this filled circle versus open circle. All right. And then you also have another function wherein if you get integration value, which is exactly equivalent to the threshold, then the output will be somewhere, which is 0.5. Exactly if it is threshold. Threshold value or greater than threshold will be same values. If it is less than threshold, will be values here. Okay, and then you have something called as unit step, which is a small variant of the same thing. you have something called as unit step function. And unit step function is equivalent to 0. Output is equivalent to 0. So towards the left of the threshold value, it's all 0. And towards the right of the threshold value, including the threshold value, wherever you have a filled circle, if it's exactly that point, it belongs to this area. So exactly if you get the threshold value, output would be 1. Output would be equivalent to 1. Or if it is greater than threshold. So greater than or equal to threshold, output would be equivalent to 1. Less than threshold, output would be 0. And then you have something called as Heaviside step. Heaviside step is exactly like unit step. The only exception is that you cannot give any threshold value that you want, like what you have done in unit step activation function. You cannot give any value of your choice, but the threshold value should be 0. And if you take the same Heaviside, if you take the same Heaviside step, then it is almost the same like your unit step or like your Heaviside step. These are exactly the same, wherein the threshold values are given as 0. However, okay, the values to the left of this, it is -1 rather than 0. When it comes to this, it is 0, right? Less than or equal to threshold equal to 0. But here, in this case, that is not the case. Okay, and we call this particular activation function as sign function. Sign activation function. Okay, then is this a linear function? Are the step functions linear functions? Let me see how many of you all understand this and answer correctly. No. These are all non-linear. These also are non-linear. Same. So these are called as non-linear steps. But piecewise they are linear. When you look at each piece, it's linear, straight line, straight line. But otherwise, it's a non-linear thing because overall it's not linear. Then there is one amazing activation function which is still extensively used. Then, and I would say this is probably the most popular activation function. For some reason, it keeps giving you amazing result. It's called as rectified. RE stands for rectified. L for linear, U for unit. So it is rectified linear unit. And when you look at this specific activation function, so again, integration or neuron will contain integration and activation. This guy will send you some information. This integration will give this activation function some number, right? If that value which comes out happens to be less than or equal to this value, whatever you get as an output, then the output would be equivalent to 0. But then, if the values are equal to 0, or greater than 0 for that case. If it is 0 or greater than 0, then the output will be 0. So if the value would be, if you get an activation function here, if it is less than or equal to if this integration component, then output is 0. If this integration component is greater than f, okay, greater than f, or whatever you get, if it's greater than x, say it is 0.8, that means y will be equivalent to 0.8, output will be equivalent to 0.8. If you are supplying this activation function some values, and if that value that you get is equal to 0.6, then output also will be 0.6. That is the meaning of Rayleigh. So negative values it will completely remove. But positive values, whatever positive value you have, exactly that would come out as an output. Then you have Rayleigh activation function. Or sorry, leaky Rayleigh activation function. People thought that if in a neuron you have integration and activation, if this integration value which is going into the function is less than or equal to 0, then you're forcing the output to be 0. However, what Leaky Rayleigh believes is the negative values also have some impact on the output. Rather than forcing all these negative values less than or equal to 0, all these negative values to 0, can we not scale it down by a factor? So when you take this integration and give it to the activation function, it will reduce that number by 10, and that becomes your output here for the negative values, only for the negative values. For positive values, it is still going to act like typical Rayleigh. If this value is 0.8, you'll have 0.8. That is, the output will be 0.8. If this integration value, which is going into Rayleigh activation function, if that happens to be 0.3, output would be 0.3. And we also have something, in Leaky Rayleigh, you scale down the negative values by a factor of 10. Reduce it by a factor of 10. But then should it always be scaling the negative values by a factor of 10? Can I not scale it down by a factor of 20, 30, etc.? That is where a new activation function was introduced, which is called as parameterized Rayleigh. Or parametric Rayleigh. Parametric Rayleigh is exactly similar to Leaky Rayleigh, with the only exception that if you reduce or if you scale down the activation values by a factor of 0.1, it's called as Leaky Rayleigh. But if you scale down by 0.3 or 0.7, then you keep getting something called as parameterized Rayleigh. You can just try out these things and see how it works. So the essential thing when we use parametric Rayleigh is to never scale a factor of exactly 1. What will happen if the factor, the scaling down factor is equivalent to 1 exactly? Then what do you think will happen? What would happen to this red line? If I say that let us scale it down, let us scale output values by a factor of 1, then how would it look like? A linear line, absolutely, right? A linear line. Because it's becoming linear and linear. If factor value equal to 1, it will be exactly a straight line. But then it becomes what? Linear. What is the disadvantage if you get linear pattern? Anyone? Your network will collapse. Your network will collapse. Means your training stops. This implies that model training stops. Then you have another variant of these things, which is called as shifted Rayleigh. Shifted Rayleigh is same Rayleigh. The only thing is you're shifting it down. Okay. Since you're taking it down, it's going on this side. We know that activation functions are going to help you identify non-linear patterns. For ensuring that a specific activation function is non-linear, you should have a kink like this. Kink. Kink means sharp bend. And then there are yet a few more activation functions. One is called as max out. When you combine Rayleigh activation function and leaky Rayleigh or parameterized Rayleigh, when you combine these two, when you combine leaky Rayleigh or parameterized Rayleigh with basic Rayleigh, that is, I'll call this as basic Rayleigh. Then you have leaky Rayleigh and parameterized Rayleigh. If you combine the basic Rayleigh with either leaky Rayleigh or when you combine the basic Rayleigh with parameterized Rayleigh, then it will create a new activation function which is called as max out. It is called as max out activation function. You have different lines, you know. This is like Rayleigh, this red line. And then your parameterized Rayleigh might give you some other value, so on and so forth. Here. If I have, okay, again, this is what we are talking about. We get some integration value because neurons will be connected to this. Randomly weights are assigned into inputs. When you multiply, you get the integration. That integration value, you supply it to activation function. If you supply it to something called as max out, then what will be the output? We'll take whatever is that value. Say this integration is giving a value of 0.8. 0.8 will be somewhere here on this. So when you scroll up, you have two lines, this and this. But take the maximum out of these two. So take the largest value of these two. If suppose this integration value was 0.5, then here you will get one value on this line, one value on this line, one value on this line. One value here, one value here, one value here. Out of these three, you pick the largest value, which is this. And that would eventually become your output. Okay. Then we also have something called as noisy Rayleigh. It's not frequently used, but it's called as noisy Rayleigh. And then you have the smooth functions, smooth activation functions. In these smooth activation functions, one of these is soft plus. But even before we get into this, I think it's high time that we take a break. And after break, we will take this discussion forward. It is 3:15 now. Let us get back by 3:30. Please take a break and come back. Let me also pause the recording. Okay, so now we are going to talk about smooth functions. Until now, these functions that we have spoken about are called as piecewise linear. What do you mean by piecewise linear? If you look at this piece, only this piece is linear. If you look at this piece, only this piece is linear. Together, when you combine, it's non-linear. But when you look at these pieces, it is linear. That is why it is called as piecewise linear. Now we are going to talk about smooth functions. Among the smooth functions, the one function that we need to talk about is called as soft plus. But why do we need smooth functions when we have piecewise linear functions? Like Rayleigh, how was it? It was like this, Rayleigh activation function. But wherever you have that sharp kink, there won't be any derivative. There won't be any slope. Derivative or slope or gradient all mean the same, right? You will not have anything. That is why you cannot find the derivative of this point. Hence, people prefer something which is smooth, something which can be differentiated. And as part of that, you have soft plus. Soft plus is typically Rayleigh activation function only. But wherever you had the sharp kink, Rayleigh was like this. So there, instead of this sharp kink, you're putting one smooth finish and you're calling it as soft plus. We can smooth out the shifted Rayleigh also. If you look at the shifted Rayleigh, this is your shifted Rayleigh, right? Same Rayleigh, we're just bringing it down like this. So when you have it in that way, it will be called as exponential linear unit. And a few other soft or smooth functions include sigmoid function. Sigmoid function is also called as logistic function, or it is also called as logistic curve. Logistic function or logistic curve. It resembles an S shape like this. It's like S. Here, whatever be the input that you give, output will lie in the range of 0 to 1. Whatever be the input, finally what it does is it will take that input and it will ensure that the values are in the range of 0 to 1. And if I have a business problem such as whether a person will default or not default, two-class problem. If you have a two-class problem, whether a person will default on the loan or not. In this case, if I have a value output, say you have the input layer, you have a hidden layer, and finally you have output layer. Here you have integration component, and then you have activation component. Finally, you get an output. Okay. Here also you have integration component and activation. Here also you have integration and activation. Okay. Now, whatever be the value which is given to your activation function, and if this activation function is sigmoid, Output values will lie in the range of 0 to 1. If I get a value as 0.8, what does that imply? It implies that there is 80% probability that a person will default. Whatever be the integration value, if I supply it to sigmoid activation function, it will ensure that the output is in the range of 0 to 1. And then here you define a rule. If the output value is going to lie in the range of 0 to 1, and these are probability values, okay? 0 to 1, probability values range between 0 to 1. And sigmoid also is going to take any input and ensure that it falls in the range of 0 to 1. Okay. And probability values also range between 0 to 1. And then here you define your rules. You say that if the output, this function value, if it is less than or equal to 0.5, less than 50% chance, then you will say person will not default. If the value is greater than 0.5, then that means person will default. Less than or equal to 0.5, not default. Greater than 0.5, default. And the values range between 0 to 1. Hence, when your output variable is discrete, and if it has two categories, then people usually use sigmoid activation function in the output layer. This is your input layer. This is your hidden layer with 2 neurons. And this happens to be your output layer. When your output variable is discrete in two categories, we use sigmoid activation function in the output layer. Also, we have something else which is called as tan H, which also stands for hyperbolic tangent. Tan H means hyperbolic tangent. In this hyperbolic tangent function, if you have input, output, and then the output layer, sorry, inputs and then hidden layers and output. Here, if you use activation function as tan H, hyperbolic tangent, then what it does is, whatever be the integration value it gets, when it supplies that to tan H, you'll get an output which ranges between 1 to -1. The value will range in between 1 to -1. Sorry, I'm having green tea just to ensure that I keep myself active. Okay. So these are all the smooth functions. If you observe carefully, they all have smooth finishes. So sigmoid takes the values, and the values can be anywhere in the range of -infinity to +infinity. And then it squashes the values into the range of 0 to 1. In tan H also, when it comes to tan H, then if the inputs are in the range of -infinity to +infinity, it will squash these values into the range of -1 to +1. Okay, so that's what is given here. So sigmoid and tan H are just compared. If it's sigmoid, right, be like this, tan H will be like this, -1 to +1. sigmoid will be 0 to 1. Okay, there is also another thing which is called as swish. If you combine Rayleigh activation function and if you combine sigmoid, then it gives rise to something called as swish, wherein you just have a small bump here, a smooth bump, small smooth bump, just to the left of 0. Just if this is 0, just to the left of 0, yeah, and then it flattens out. Okay, so these are the benefits of the various activation functions, but there are a few things that we need to understand. Rayleigh and the family of Rayleigh, that is ELU or soft plus, etc., are very widely used. For some reason, when you use Rayleigh activation functions in the hidden layers, not in the output, in the hidden layers, when you use Rayleigh activation functions, it gives you the exceptional results. Of course, in input layer, we will not have any activation functions. Only in hidden layers and output, you'll have activation functions. Okay. And in hidden layers, usually when people use Rayleigh, it was giving highest accuracy. So people are sticking with Rayleigh. Okay. But then the disadvantage with Rayleigh and family is that whenever you have a sharp kink, it doesn't work well. That is when people prefer sigmoid or tanh activation functions. Okay, this is one thing that you need to remember. And also in the output layer, if the output variable is continuous, in the business problem, say you're trying to predict salaries of people, which is a continuous output variable. When you have output variable which is continuous, we prefer linear activation function, which is also called as identity function. Simply put, if you don't mention any activation function, it is considered to be identity or linear. If you don't use any activation function, it is equivalent to using linear or identity function. Okay, please bear this in mind. Next, if the output variable is discrete in two categories, then you end up using, okay, if the output variable is discrete in two categories, then you end up using sigmoid activation function mostly, or tanh. But most preferred is sigmoid. Between sigmoid and tanh, people prefer sigmoid. Now, there are also disadvantages with respect to smooth curves. What are the smooth curves? Rayleigh belongs to something called as piecewise linear. And you also have smooth curves. When it comes to smooth curves, you have something called as sigmoid, you have something called as tanh, etc. These will always give you back the same value, right? This will always give you values in the range of 0 to 1. This always gives you values in the range of -1 to 1, no matter what the inputs are. This phenomenon of taking any value and always giving you the output within a specific range, like 0 to 1 or -1 to 1, this is called as saturation. Okay, this is called as saturation. Okay, so this is how it works. And what will happen if it is saturated? If the values are saturated, derivative of that will go to 0. Derivative of that will always give you 0. If the derivative becomes 0, that means your training will stop. Please look at certain things that I'm going to write here. So all I'm saying is, if you have a curve like that, remember one thing, that derivative of a constant, any number, say 1, 2, 3, whatever, is 0. Derivative of any number, say 0.8, is 0. Derivative of any number is 0, of a single value. If the derivative becomes 0, what is derivative also called as? Gradient. This is also called as slope. This is also called as rate of change. If the derivative becomes 0, your algorithm will stop. If randomly your weights are assigned somewhere here and you update it to update your loss, again when you update, say your derivative, say you used sigmoid or tanh activation functions in the hidden layers. If you use it, what will happen? During the training, sigmoid or tanh will ensure that it takes the inputs and squares the values into range of 0 to 1 or -1 to 1. So it will stop. Right? The training will stop because you get a single value. Eventually, the training will stop. Right? When the output is the same value, that means there is no change. It's the same. There is no derivative. It will remain the same. Right? If whatever values you give as an input to sigmoid or tanh, if you keep getting the same value, then it will be the same. There won't be any change. Slope will be same. That means derivative is 0. Rate of change is 0. And the similar kind of problem is faced for negative values when you have Rayleigh. Because Rayleigh activation function looks like this. Here you have 0, here you have negative values on this side. And on this side you'll have positive values. To the left of 0, it's all 0. If you look at this output, this is 0. To the left of 0, it's straight line, it's all zeros. So similar kind of saturation problem arises when it comes to negative values of Rayleigh. Okay, so that's, I mean, every algorithm has certain pros and cons. But when it comes to the positive zone, there are no such issues. Okay. So we have spoken about all these things. Now we need to talk about one more activation function, which is called as softmax. Just remember that when your output variable is continuous, we use linear or identity. That means don't use any activation function in the output layer. In the output layer, don't use any activation function if your output is continuous. If your output variable is discrete in 2 categories, use sigmoid. If you have more than 2 categories, if you have output variable which is discrete, and if it has more than 2 categories, then what happens? If you have more than 2 categories, say 3 categories, say you have a 3-class problem. Given an image, classify whether it is a cat or a dog or a lion. 3 classes. In your neural network, You have your input, say you have your output. You have your hidden layers, and then say you want the output. Just for understanding, you can put more nuance. And then say you have your output. Since you have three classes, you need to have three neurons in the output field. Since you have three, you'll have three neurons. That is what we have spoken. But the outputs that you get here, say you got a value as 0.8, you got a value as 0.6, you got a value as 0.7. When you add all these values, you get what? 2.1? Yeah. What is the rule of probability? The rule of probability is that when you add all the values, it should be equivalent to 1. Only then can you say that if this is for cat, if this is for dog, and if this is for lion, then there is 0.8% probability that it's a cat, 0.6% probability that it is a dog, 0.7 probability that it is a lion. Any image that you supply, you get these predictions out. But when you add these values of a neural network output, it will not be equivalent to 1. That means these values are not normalized. These values are not probabilities. This is where people add an activation function called as softmax. So it will take these scores like 0.8, 0.6 and all that. And then when you apply softmax activation function, it will convert these numbers into something else, which will actually give you probabilities. So maybe it will say that this is 0.55. It might say that this is some other value. And ultimately, let me tell that this is 0.4. This might be 0.05 or say 0.3. Then it will be 0.15. Okay. So now if you add these values, it will sum up to 1. So the softmax applies some math equation on it, on the outputs of the neurons. It will apply some math equation. And finally, the results will be probabilities. How can you determine whether those are probability values or not? Just add them up. If they sum up to 1, then those are probability values. Fine. So you might feel that, oh my God, nothing to worry. As I've told you, if you are writing a running notes while I'm teaching you, if you are writing on your book everything that I'm explaining, while I'm teaching, in parallel do it, then at least 40% you'll remember. At least, minimum this much you'll remember. This is more than sufficient. Don't aim for 100%, doesn't happen. Once you watch the video once again, you will get to 60% zone. And watch it third time, you'll certainly hit 80%. And that is all that is needed for you to clear interview. Okay, this is all that is needed for you to clear the interview. Okay. Now also make use of mind map without fail. And here when it comes to activation functions, you have everything listed down. What is linear function? Output continuous, use this. Is also called as identity. Then you have step functions, state step, unit step, heavy side step, sign function. Then you have ramp function. Then you have piecewise linear, Rayleigh, and the family of Rayleigh. Right? Then you have smooth functions, soft plus. What are those? When output variable is discrete, in 2 categories you use this. Okay. ALU is another thing, squish. Then you have max out, then you have soft max. When you use it, Everything is given here, friends. So if you go through this, then things will be extremely good. And all these sessions would be recorded, and the link of this would be placed on your learning management system as well. So give yourself a good compliment because you have covered great bit of things until now. So now we will get into the next zone of discussion. So let us understand multi-layered perceptron boundary. This part I'll just skip and then I'll get to this, and then we'll also look into, yes, there is a demo which is coming up. So this is how your error surface looks like, or I would rather call it as loss or cost function. This is how it looks like. If you have two weights, if you have two inputs in your data set and an output, then you will have two weights. Or even if you have a single input, you can, I mean, here I'm ignoring bias. If you want to consider bias, then even if you have a single input, you'll have a bias. Now, if weights are randomly assigned here, then weights will like this come down, come down, come down, and go to the minima. Or if your weights are randomly assigned here, it will come down slowly and reach the minimum. So, which minima will you reach really depends upon where the weights are initialized. You know that weights are randomly assigned. If the weights are randomly assigned somewhere here, it reaches this minima. If the weights are randomly assigned here, it reaches this minima. If the weights are randomly assigned here, it will reach this minima. So based on where it randomly is assigned, it will reach one of these minima, which is listed down here. Okay, if it starts here, slowly it will reach here. Right? For example, this is how it works. You have the parameters. Parameters are weights. Weights or parameters mean the same. Okay. And suppose this is a place where the weights were randomly assigned. Starting point. And the associated losses here. Then, as part of your back propagation, the weights are updated. And say weights are here. Then the loss is this. So the loss reduced. Then again, if you update your weights, the weights will further get reduced. If you again update the weights, loss will further get reduced and it will reach your minimum. After that, if you update the weights, your loss value will increase. The moment your loss value increases, you stop. Okay, you have to stop and say that, yep, I've reached the minima, so I'm going to stop the algorithm. Same thing. If your weights are randomly assigned here, then you update the weights, minimize the loss. Update the weights, minimize the loss. Update the weights, minimize the loss. Update the weights, minimize. Update, minimize. Ultimately, you reach the minimum. If you have an error surface like this, just like that, then you reach the minimum. If your weights, okay, you reach the minimum like this. But usually your error surfaces or loss surface or cost surface would not be like this. It look like this, like a Himalayan mountain range. So you really don't know where you're going to land. It really depends on where your weights are initialized. So if your weights are initialized here, you'll get to this minima. If your weights are initialized here, you'll get to that minima. So it really depends on where your weights get initialized. It depends on that. Depending on that, you reach one of the minima. Now let us understand this backpropagation algorithm. Okay, and of course every neuron will have integration component and this activation component. But what we are doing is, for our ease of understanding, and just for demonstration only, for visualization only, I'm just representing both of these integration and activation combined as function. So this is the kind of setup that we have, wherein say you have one output variable and you have two inputs. And you have various observations. Say you have 10,000 observations. Maybe the output is to predict salary of a person based on age and income. X1 is age, income. You have age and income, and then you want to, not income, sorry. What am I thinking? Age and graduation. Whether that person is a diploma holder or a graduate or a postgraduate or a PhD or postdoctorate, you have all the education levels. Based on age and education, you need to predict salary. So this is your data set. And number of hidden layers is something that you can decide. Since you have two inputs, you have two neurons. Of course, there will be one more neuron called bias. For now, we will keep that bias aside. Okay, that bias, we will keep it aside just for our understanding. And then you have all these neurons, wherein you have two components. Integration, activation, integration, activation. Every neuron will have integration and activation. Here you are having two hidden layers. One hidden layer is having three neurons. Another hidden layer is having two neurons. Okay, one hidden layer is having three neurons, another hidden layer is having two neurons. And finally, you have an output. So, let's do the demonstration here. So if you have inputs, what will happen? First time, the weights are randomly assigned. The weights here are randomly assigned. So you have these weights. And this contains what? Two components, right? It contains integration and activation. So W1 into X1 plus W2 into X2 would give you the integration component, this component. And then you pass that to the activation component. Some activation function, say you're using Rayleigh, then you get an output, Y1. So let me see that you have an output here. Next. This also will have integration and activation. W1x1 plus W2x2, that will give you the integration component. You take that and pass it on to the activation component. Then you get Y2. Then, say you have two more weights. This weight into this input plus this weight into this input will give you integration component. Pass it on to the activation component, and then you get Y3. Now what you do is, again, here also weights are randomly assigned. So this weight into this Y1 plus this weight into Y2, this weight into Y3 will give you the integration component. Then pass that integration to the activation component and you get an output. Here you are getting something called as Y4. Then weights are again randomly assigned. This weight into Y1, this weight into Y2, plus this weight into Y3 will give you the integration component. Take that and pass it on to the activation component. And then you get Y5. Okay. Then again the weights are randomly assigned. So this weight into Y4 plus this weight into Y5 will give you the integration component. When you pass it to the activation component, 6, you get the output. That is a final output. That is a predicted value. Okay, this is your predicted value. The moment you get the predicted value, what should you do? You have to look at your database. Okay, you have your data, right? Output and inputs. And then say you have 10,000 observations. Say you're taking the first row and passing through your network, forward pass. You've done a forward pass. And then you got a predicted value. Now take the actual value here and see whether the predicted value and actual value are the same or not. If they are not same, subtract them. So you're saying actual value minus predicted value. If there is any loss, then what you need to do is go back and update the weights. This process of coming forward, calculating the loss, going back and updating the weights is called as backpropagation algorithm. Backpropagation algorithm. And why are you updating the weights? We are updating the weights to minimize the loss. The algorithm which is used in the process of minimizing the weight is called as gradient descent algorithm. Gradient descent algorithm, which will minimize the loss. Okay, next. Now we need to go back and update the weights, right? So how does the weight updation happen? Yes. So here what we are doing is, this is like a manager concept weights. If you have a manager, okay, and if the board of directors say that, you know what, because of you, there was a mistake which happened on the project. Error is that only, right? Error means something went wrong. Loss means something went wrong. So because of you, we experienced a loss. So we are going to deduct your bonus component, or we are going to deduct your incentive, variable pay. If they say so, then this manager will go back to the team leads and say that, my dear team leads, because of you all, project went wrong and my bonus or variable pay is deducted. So I will also penalize you, team leads. Usually that's what happens, right? So this manager goes back to the team lead and says that, boss, for me, this error component, that much proportion bonus they are removing, deducting. So I will also put a penalty. This team lead will quickly say, manager, I've given you only W46 information. Okay, then you'll say, okay, take back that much amount of penalty. That much amount of your variable pay will be deducted. So you say error here would be, or loss here would be this much weight into this error. That much penalty you are giving back. Then you also go back to this team lead, F5, and say, what about you? This guy also will say, you know what? I supplied you only so much of information, this much weight. So that much weight of this error, take back as penalty. Then will the team leads keep quiet? No. They are like, team members, because of you, our bonuses are deducted. So we'll also put a penalty on you. And these team leads will go back. This team lead F4 will go back and see who are the team members who have given inputs. F2, okay, has given input to F4 and F5. This team member will say, do you know what? I work for both of you team leads. W24, I gave it to F4. So this F4 will say, W24 into this error, take as penalty. And F2 will say, W25, I gave it to you. So F5 will say, W25 into this error, summation of that will go as an error penalty on you. Giving penalty. Again, F3 will say, I gave you inputs. W34 to you, W35 to F5. So W35, so W35 into this, W34 into this, plus W35 into this, take back as penalty. So that penalty, let me select the eraser, I think it's fine. Yeah. That's fine. All right, now you go back to the next guy, to this guy, and then keep updating in that way. So after you update the weights of, or if you give, after you give back penalties to everyone, then what you do now is you update the weights. And the formula to update the weights is new weights is equal to old weights plus eta value into your error into your input. This is what was the formula that we have used. So new weight equal to old weight plus eta value into, this will give you error into input. Derivation. Derivation or gradient or slope. Derivation or gradient or slope. You keep reducing. That's why you take a differentiation derivative. This is how you again keep updating all of your weights. For all weights. All weights are updated in similar fashion. Old weights equal to new weight plus eta value into error into input. Do that continuously and then again calculate the output. Again come forward, go back, update the weights. So keep doing this process. And we already discussed about what is epoch, what is iteration, etc. Okay. So now we have network topology that we need to talk about. In this specific representation of network, you have input layer, and then you have a hidden layer. This hidden layer has 3 neurons, and then you have your output layer. This output layer has 2 neurons. Here you have multiple output nodes. And here you have multiple hidden layers. So you have your input layer. You have 2 hidden layers, hidden layer 1 and hidden layer 2. Each of the hidden layers have 3 neurons each. And then you have your output layer. So the network topologies might vary. You might have different network topologies. I have a basic question for you. If I have a data set and a neural network architecture like this, what is this called as? Perceptron or multi-layered perceptron? Given the understanding that we are until now. Is it called as perceptron or multi-layered perceptron? What do you guys think? It is perceptron. Why is it called as perceptron? Because in a perceptron algorithm, you will not have any hidden layers. Here, do you have any hidden layers? No. And you will have a single neuron in output. If you have a single neuron in output, and if you do not have any hidden layers, this is called as perceptron algorithm. And then you have multi-layered perceptron. When it comes to multi-layered perceptron, you will have hidden layers also. You can have one hidden layer or two or multiple hidden layers. In each of those hidden layers, you will have certain neurons. And then you have output layer. You can have either one neuron in output or multiple neurons. Okay. This is called as multi-layered perceptron. Perceptron algorithm can handle linear patterns. Multi-layered perceptron can handle non-linear patterns. Okay. Now, okay, a few things are there. Let's quickly talk. The world started off with Torch, then Theano came in, then Caffe, then TensorFlow. Before TensorFlow, Keras came in. Now we have PyTorch. A lot of deep learning libraries support graphical processing units and also tensor processing units. The beauty is that graphical processing units and tensor processing units will perform the operations faster. But today, as we stand, we have PyTorch, which is awesome, amazing. Right. New kid in the street in the space of deep learning. And when you look at various deep learning libraries for that case, okay, this is something where you're saying that Keras is a high-level programming language. When you write your program in Keras, it will convert that into TensorFlow, which is a low-level programming language, and then it executes the code on either a CPU or a GPU or a TPU. Whatever you use, it will execute on it. And here are the bunch of libraries based on the demand. Though you might see scikit-learn, TensorFlow, Keras, XGBoost, etc. PyTorch is here. But then today as we stand, this is 2 years old screenshot. Today as we stand, PyTorch has surpassed a lot of competitors. Okay. Is deep learning a holy grail? Means, will deep learning solve all the problems? Then why should we learn other algorithms? Can we not learn only deep learning algorithms? Right? So the answer is deep learning algorithms are not holy grail. Deep learning is not a silver bullet. Okay. So most loss functions are non-convex in parameters. That means when you look at various loss functions, they appear like that. Okay, it will be non-convex. Next thing is, that means if the weights are initialized here, you'll get to this minima. If the weights are initialized here, you'll get there. If the weights are initialized here, you'll get there. And also, I mean, most loss functions are non-convex. That means different initializations, different weight initializations will result into different minimas that you're going to, arrive at. And it also doesn't have interpretability because these are black box techniques. Interpretation does not exist. And when you deal with financial services insurance or life sciences healthcare, then interpretation is mandatory. Then you have a lot of ablation methods, meaning deciding different arguments like number of hidden layers or number of neurons within a hidden layer. All these things, there is no science behind it on what values you need to choose. I can choose 100 hidden layers or 20 hidden layers. In each hidden layer, I can have 10 each, or it's up to me on how I can experiment. Those are called ablation techniques, not very clear scientifically. And there is no explainability. You cannot explain your model to the outside world. And another thing is lack of easy reproducibility. Meaning, if I run the algorithm now, since the weight initialized here, I might get this loss and accuracy might be better. Next time, maybe weights are initialized here, so I'll reach this minimum. So I'll get less accuracy. So you cannot reproduce the results easily. So it is always better to use a standard toolkit or a library of framework to try to some extent. And explainability, DARPA is working on it to bring in a lot of explainability. US Department of Defense has this unit called as DARPA. Despite all these things, deep learning is most widely used algorithm today because it can handle videos, it can handle images. Videos or images mean the same in the context of deep learning. Anyways, video has to be broken down into images, right? And then you'll have audio files, you'll have textual data. No matter what data you have, ultimately, if you use deep learning algorithm, deep learning algorithms will learn the features. Features are like inputs, and then it will give you the output. So when you have very complicated data, too many columns, too many rows, wide variety of data on videos, images, audio files, textual data, then you use your deep learning algorithms and it will give you amazing results. Okay. That's how it works. And now, key takeaways. We understood about activation functions. We understood about how multi-layered perceptron works using a demonstration as part of our discussion. Now, we shall jump into practical challenges. And we'll talk about a lot of practical challenges and how to overcome those challenges. And in the due course, we'll also talk about a lot of regularization techniques, and we'll talk about gradient algorithms, gradient descent algorithms. This is what we shall do. So, now let us enter into the zone of deep learning challenges. We will talk about a lot of amazing things as part of this. So I'm just skipping that agenda because a few things we have already covered. What are the various things which are empirically determined. Empirically means randomly determined, right? We experimental. Number of hidden layers, number of neurons in the hidden layers, what activation functions should be used, what loss functions should be used, what gradient descent algorithm should be used. All these are experimental in the world of neural networks. Deep learning. Deep learning means neural networks. So even before we proceed further, I wish to take your attention to this thing, which is okay. This slide is very important for us. If the output variable is continuous, for model evaluation purpose, we use these accuracy measures like mean error, mean absolute error, squared error, root mean square error, etc. And correlation coefficient. When it comes to optimization, we use loss functions or cost functions such as mean error, mean absolute error, so on and so on. When it comes to output variable being continuous, you'll have a single neuron in the output layer. And we use linear or identity activation function. That means you don't apply any activation function. And it will be called as linear or identity function. If the output variable is discrete in two categories, will a person default on the loan or not? Do we have cat or a dog in the image? Is an image cancerous or non-cancerous? So on and so forth. Then for model evaluation purpose, we use confusion matrix or cross table or contingency matrix. And when it comes to loss function, we use binary cross entropy. Either you use a single neuron or it doesn't matter, right? And when it comes to activation function, we use sigmoid or tanh activation function. If you have an output variable which is discrete in more than two categories, again, for model evaluation, you can use these. For optimization, we have something called as categorical cross entropy. If you ask me, is this the only loss function, cross entropy, or do we have anything else? Then I would say there are many other things, but these are most widely used. And for example, if you have 10 classes, then it's called as 10 class problem. And when it comes to activation function, we end up using something called as softmax. This is something that you need to remember. Standard things. These are all very standard things which are used. Back to our discussion. Gradient primer. Meaning, what do you mean by gradient, so on and so forth? Derivative or gradient or slope or rate of change all mean the same things. All of these mean the same. It tells us about the shape of the curve or surface, error surface, loss surface, etc. And it will let us know on whether to move to climb uphill or do you need to slide downhill. This information will be available. And these curves or surfaces should be continuous. It should be smooth. That means you should not have any kink, no kinks, no sharp points, and the curves should be single bounded. What are the various things that are getting violated? So curves should be continuous. Is this continuous? No. It's coming like that, and there is discontinuity from here to here. Again, there is a curve. It should be smooth. Okay, it should be smooth. There should not be any cusps or sharp points. But here you have a sharp point. If you have a sharp point, there are disadvantages. We'll talk about it. And the curves should be single value. So look at this. For a specific value here, when you look at the output values, it can be this, or it can be this, or it can be this. So values vary. It can be any of those. And in a specific curve, you can have multiple minimum values. Out of all these, the value which is the least is called as global minimum. And you have a lot of maximas. Out of all these maximum values, the one which is the maximum of all is called as global maximum. Okay, these are called as local minima. These are called as local maximum. So consider a specific point on this surface here. With respect to this point, this point is maximum. And with respect to this point is minimum. So what happens is you try to look at your neighborhood across a specific point and then try to draw lines like this. These are all slopes, tangent lines, slopes. You'll understand the movement in which direction it has to move. Now, if you have discontinuity in the curve, then one curve is saying go in this direction, another curve is saying go in that direction. So which direction should I go? Algorithm will be confused. Hence, the curve should be continuous. If you have a cusp or a kink, a sharp point over there in your curve, then your slope doesn't know whether it has to go in this direction or this direction, rate of change, in this direction or that direction. Your algorithm will be confused and it will throw errors. At the same time, for a specific point, should this be the loss value or should this be the loss value or should this be the loss value? Your algorithm will be again kind of confused because it doesn't know should it go in this direction or this direction or this direction. So you get error. Same is the case with this also. For a specific value, should I choose this or this or this? If you have a vertical line, it will be completely confused. So your curves should not follow any of these patterns. Your curves should not follow any of these, shapes. Next. Because of the virtue of the formula, which is new weight is equal to old weight plus eta value into error into inputs. Because of virtue of the formula, what happens is, when you are at the top of the hill, you moved on by a big margin. The big margin you move on. Then you moved on by a slow margin. As and how you come down to a smooth surface, the amount of movement will keep decreasing. The amount of movement will keep decreasing. And eventually you get at a flat surface. So that's what happens. Just remember this. When you are at a height, you come down faster, but as and how you come down to the slope, you gradually, maintain your speed and you stabilize. Here you have a minimum. Then here you have a maximum. The one which is at the bottommost is minima, the one which is at the highest is maximum. Sometimes you can have a surface like this. flat surface. This is called as plateau. Getting stuck at a plateau is not good for your model. Why? We'll talk. Why is that the case? We'll talk in the subsequent slides. And then there is also something called as a saddle point. Saddle point means this is like a saddle that you put on top of horse. If you do horse riding, you put the saddle on top of your horse. And then on one side, if you view this from this side, it appears as if it's a minima. If you look at this from this side, it appears as if it is a maxima. The same point from here, okay, it will appear as if it's maxima. If you view it from this side. Okay, so you don't want to be stuck in a saddle point, because if you're stuck in a saddle point, you really don't know whether that point is minima or you really don't know whether that point is maximum. Next, we have something called as error function. When you look at mean squared error, you have your predicted value minus actual value, and you square it, and you take an average of that. This, if you have a single value, if you have a single value, basically single observation, this is how you calculate. If you have m number of observations, then you say divided by m. And you also have something called as a decay parameter. Just bear this in mind. Again, we'll talk about it in detail. Decay parameter, decay term. You will have L1 weight decay, L2 weight decay, etc. We'll talk about that. Just bear with me. We'll certainly talk about that in detail. And then we have something called as a vanishing gradient and exploding gradient problem. Let me explain this. What happens is you will have a network like this. And the weights are randomly assigned. All these weights that you have are randomly assigned. And if you have weights which are randomly assigned, and if all of these weights are, say, greater than 1, all these weights are randomly assigned, and if these weights are greater than 1, then what happens? Say you have a weight 1.1, which is greater than 1, and you have another weight which is, say, 1.2. What will happen here in your network? It is all multiplication and summation. When you multiply these two, the resultant will be 1.32. So when you multiply these two, you get a value which is greater than these two numbers, which is greater than 1.1 and 1.2. And if you have another number which is again greater than 1, probably you get 1.43, not sure. But then, yep, that will be even more. Okay. So the point that I'm trying to drive here is that if you have values which are all greater than 1, at some point of time, the end value will become very large number. And then what happens is, on your error surface, if it's like this, if you have a very large number, it might jump like this. Ideally, what are you expecting? If you are expecting that to come down to the minimum. But because it's getting exploded, All the values are greater than 1. So when you multiply, you get a very big number. So it's going to jump like that. And if you have a number which is small, then what will happen is, small in the sense if you have values smaller than 1, less than 1. Like say you have a number 0.9 and say you have a number 0.8. When you multiply these two, you get a number which is smaller. You get number 0.72. You get a smaller number. And again, if you multiply it with a value less than 1, you get again smaller value than this. In this scenario, you will experience something called as vanishing gradient. That means it will keep updating in small values and then it will stop, vanish. Rate of change or gradient will vanish. This is also another challenge. We are discussing about a few challenges. Okay. Next. Saddle point and all we have discussed, right? Learning rate. If the learning rate is too big, learning rate or eta value, we know for a fact that it ranges from 0 to 1. If the value, learning rate value is too large, then it won't go to this minima. It will jump to another value. If the learning rate value is too small, then it will take far too many steps to reach the minimum, take too much of time. And also it will reach a minima which is not that good, because this is a better minima, but it will end up here. So you need to choose right learning rate value. This is also another challenge. There is again a challenge with respect to learning rate or eta value, which ranges from 0 to 1. If you choose a constant learning rate, meaning throughout the model, back propagation and updating weights and all that, if you choose a constant learning rate, what happens is, wherever there is a flat, somewhat flat surface, the learning rate will be small. Where there is a steep, the learning rate will be large. And then at the bottom, what happens is, it will keep bouncing around the ball. It will go there, it will come here, it will go there, it will come here. It will never reach the minimum. This is called as bouncing around the ball problem. So what will happen? To come down, again increase, come down, again increase, come down, again increase. That's how it will be doing. So this is called as bouncing around the bottom of the ball. This problem arises when you use a constant learning rate. To counter this, people have come up with something called as changing the learning rate over time. Rather than use a constant learning rate, they started using changing learning rate. And they thought, let us do one thing. At every step, that is after every epoch, or after every iteration, when the weight gets updated, let us reduce the learning rate. You can probably start with a learning rate of 0.1. Then at every step, multiply the learning rate with a value less than 1. Like take 0.99, multiply it with. Now earlier learning rate was 0.1 for one step, one iteration. Now it has become 0.09. For the next step, again multiply this with 0.99. And then you'll get another value which is 0.09801. Again for the next step, multiply it with 0.99. This is called as changing learning rate over time. When you do this, bouncing around the ball problem will move away. If you use this constant learning rate, you'll experience that bouncing around the ball. But then when you use a shrinking learning rate or changing learning rate, this changing learning rate is, if you choose a value which is less than 1, then it will shrink, it will reduce. So that at that point of time, the advantage is that the bouncing around the ball problem is gone and it will reach the minimum. Okay. This changing the learning rate, the changing learning rate is also called as decay parameter. And decay parameter, again, we have challenges. Look at this deep learning. That is why people are paid more, right? Here also we have challenges. What are those challenges? Which one should I use? Should I use exponential method, wherein I exponentially keep reducing the learning rate? Or should I use a variant of exponential learning rate, wherein for a few epochs, I will let my learning rate be constant. And after that, I will start exponentially decreasing my learning rate. Or should I use step approach? In step approach, for 4 epochs, I won't change the learning rate. Again, I'll drop the learning rate. For the next 4 epochs, I'll not change it. Again, I'll drop it. For the next 4, again, it will be the same. Then again, I'll drop it. Next 4 will be the same. Again, I drop it. This is called as step method. And then you also have bold driver approach. In bold driver approach, as long as the error is reducing, you let your learning rate be the same. Learning rate value will remain the same as long as error value is decreasing. The moment your error becomes stable, okay, the moment your error becomes stable, you will change your learning rate. You reduce your learning rate. Then as long as the error is decreasing, don't change the learning rate. But the moment your error is becoming stable, change the learning rate. That's how it goes. Okay. Those are the challenges. Now we have something called as algorithms, right? Gradient descent algorithms. Gradient descent algorithms are used to minimize the loss or cost. That's the purpose of gradient descent. Gradient means what? Rate of change. Descent means downward direction. So if you are moving the rate of change in this direction downward, it's called as gradient descent downward. And all these three we have already discussed: batch gradient, stochastic gradient, mini batch gradient descent. In all these three, okay, all these things also we have discussed. Basically, we know loss function, activation function, what is iteration, what is epoch, what is learning rate. We spoke about all these things, right? And we understood about batch gradient descent. Batch gradient descent is also called as offline algorithm. Just remember that. Then you have stochastic gradient descent, SGD. Okay, you randomly shuffle, and this is called as online algorithm because immediately you are updating online. Immediately you are updating. In batch gradient descent, there is a disadvantage. If you run all your data, if you have in your data set, say you have output variable and input variables, and say you have 10,000 observations or 100,000 observations. If you pass all these through your neural network, and if you want to save all of these loss values, then you need sufficient memory. All these weights have to be stored, loss values, sufficient memory should be there. If you don't have sufficient memory, you'll get errors. Okay, that's one disadvantage because you're passing all these 100,000 examples through your neural network and storing all the predicted values, calculating the loss, and then you're storing it. So it will be very time consuming. So SGD is there, which is online algorithm. And then you have mini batch SGD. As I've told you, usually the batch size is preferred to be to the power of 2, like 2 raised to the power 4 or 2 raised to the power 5, 16, 32 is what you get in that. Because usually when you look at your RAM, you'll have 8 GB, 16 GB, 32 GB, 64 GB in that. Challenges. There are challenges with respect to mini batch SGD. Out of all these, mini batch SGD is considered to be the best. Out of these three, mini batch SGD is considered to be the best. But then, mini batch SGD also has challenges. Here we have to specify what learning rate value we want to use. And it's difficult to pick. If you choose a value which is too low, long learning rates, and then you can get stuck in a shallow minima, meaning if your weights get initialized here, you end up here. If you use very small learning rate, there's no chance of you coming here and then slowly getting to this minima. There's no chance. If the value is too small, if your weight gets initialized here, it will overshoot. Either way, it is a challenge. It's a double-edged sword. And then we can, if you try to avoid this problem by using decay parameter to change learning rate over time, what decay schedule will you choose? Exponential, delayed exponential, step, or bold driver? Which technique will you apply? Again, bunch of things are there. And to pick the mini batch size, again, it's a challenge. What should be the batch size? 128, 256, 512. What should be the batch size? Now here, the challenge with all these SGDs is that we are using the option of one update rate fits all. Meaning, when you update the weights, in each and every place, we are using the same formula to update. What is that formula? New weight equal to old weight plus eta value into error into input. Right? Same formula is being used to update all the weights in your neural network. If you have one weight here, same formula is applied. You'll have a weight here also, same formula is applied. This weight, this weight, this weight, this weight, this weight, and this weight. For all of these weights, we apply the same formula. How to overcome these challenges? To overcome these challenges, we have something called as momentum, Nestor Momentum, ADA grad, ADA delta, RMS prop, Adam. We have all these algorithms which are used to overcome the challenges of mini batch SGD. Friends, to remember all these things, right? Remember it as a story. All these slides, just stitch it as a story, and then you will start remembering. If you use learning rate, very small, then also it's a challenge. Very large, then also it's a challenge. So to overcome that, we can use decay parameter. In that, again, you have 4 to 5 options. Which option should we choose? Again, that's a challenge. Then we have gradient descent algorithms. Batch gradient, stochastic gradient, mini batch SGD. Mini batch SGD is the best. But again, it has its own challenges. That the same formula to update the weights is applied to all the weights. To overcome these challenges, we have all these options: momentum, Nestor momentum, ADA grad, ADA delta, RMS prop, and ADA. Okay. So let us at least get into one or two talk and then we will stop. So before that, I mean, this is a new thing that we need to start. Let me take quick 10 minutes break and then we will take it forward. I know I'm taking far too many breaks, but there is a reason why I'm doing that. Because otherwise you might find it very, very difficult to remember. So let us be back at 5:15 break time. Or let us be back at 5:20, please. At 5:20, we'll come back and take this discussion. Please take a break and I'll pause the recording. Okay. So let us take this discussion forward and talk about momentum. Sorry, just give me a moment. Okay. So friends, what do you mean by momentum? And let us understand more about that. Oh, sorry, just allow me a quick moment. Switch on this. If you have a surface, loss surface like this, and if you are minimizing the loss, and if you reach this surface, which is flat, okay, if you reach this surface which is flat, what happens? If you have a gradient descent with decay parameter, we discussed about decay parameters, that is changing learning rate or shrinking learning rate. Okay, that's called as decay parameter. So here what happens is in this surface, after it reaches here, it will try updating, and then after a few iterations, there won't be any major change in the loss. So your algorithm will stop. So your gradient descent will stop. So gradient descent will decay. Because if there is no major change, why should your algorithm continue to run? But what if you have a surface like this? What if instead of stopping here, if your algorithm moves slightly here, then you can reach a better minimum loss. But how? How can I reach there? For that, there is something called as momentum. Momentum is some kind of a push. Right? Imagine a ball that you're rolling, and if the ball comes and stops there, finish. Algorithm stops. But if you can allow this ball to gain some momentum so that it moves further and reaches a minima, then amazing. That is the basic concept of momentum. So it reaches a better minima rather than stopping here. If you only use a decay parameter, it will stop there. Shrinking learning rate. Learning rate keeps reducing, so your algorithm will end there. But if you give it a momentum, it will move ahead and reach a better minimum. So momentum helps us get over flat plateaus and wherever you have shallow places in saddles. Saddle is from one direction it will look as if it's minima, from another direction it will look as if it's a maximum. Okay, next. You have something called as Nestor Momentum. In Nestor Momentum, you understood the concept of momentum, right? We give it an additional push. And to talk more about this momentum, I think I need to talk more about this thing called as momentum, right? Just to help you guys understand even better. So I'm just wondering on what all should I cover as part of this. Okay, that's okay. I'll probably talk about a few additional things in momentum. So what happens in momentum is you choose a specific parameter. Okay, you tend to choose a specific parameter, and that parameter is called as gamma value. Gamma. That's how it is denoted. It's a Greek notation. We multiply the momentum value. Momentum is some push that you're giving. We multiply this momentum value, and you multiply it with a parameter called as gamma, which is also referred to as momentum scaling factor. And this value ranges from 0 to 1. Similar to learning rate, this also ranges from 0 to 1. Now, suppose that your algorithm is here. Your weight is here, A, which we updated to make it B. Okay, we updated to make it B. We now want to find the next value of the weight. Next value of the weight is, if this is A, if you want to be at B, okay, and then if you again update the weight, you'll be at C, so on and so forth. But to find this value C, what you do is, we find the change that we apply to point A, okay, which has brought us to B. We'll try to understand this. If I move it from A to B, to move it from A to B, how much change did you apply? That change, we call it as M. From A to B, if I want to move, okay, that change is given using M. This M value is multiplied by gamma. And this gamma value ranges from 0 to 1. So you first find the gradient at, now you find the gradient at B and scale it by a learning rate. You find the gradient at B. Gradient means rate of change at B, and you scale it by a factor called as eta, which is learning rate. Now, starting at point B, we add this scaled gradient. Suppose the gradient at B, rate of change at B, from B, if I move, what will be the rate of change, right? Say that rate of change is, the gradient value is G. So you multiply this eta value learning rate with G. At point B, you find the gradient. Multiply it with your learning rate. Now, at the same point B, we add the gradient with the previous step momentum. Previous step momentum into gamma. You add these two, and these two are added at this stage, and that will move you to C. Okay, so suppose I'll repeat this part for everyone's understanding once again. And let me choose a different color. Suppose you have point A and point B and point C. Say you are currently at point B. This is a present point we are at. We look back at the previous point A and we look at from A to B. Okay, to move from A to B, what was the change? What was the gradient change? We call it as M. That's called as momentum. What was the change? And we multiply it with momentum scaling factor called gamma. And gamma value ranges from 0 to 1. Keep it aside. M gamma, you calculate it, keep it aside from the past. Now, at point B, if you want to go with your regular gradient descent algorithm, you might be at C. You might be at C if you go with your regular gradient descent algorithm. And here also, let me call this gradient as G, the change. But then you also multiply it with the scaling factor, which is nothing but learning rate. If you multiply the learning rate with gamma, you will be at C. But when it comes to momentum, that is not what we do. We also take the previous step, momentum value, which is scaled by momentum scaling factor, and add it here. When you do this, both of these changes will get applied onto this point C, onto this point B, and the new point C might be somewhere here. It need not be this, it will be somewhere else. And that would actually help you move like this. So you're giving that additional momentum. That additional momentum is coming from the previous change, the previous gradient into the momentum scaling factor. That would actually help you move to a new point altogether. Then you have something called as Nestor Momentum. What this Nestor Momentum does is, it says that, do you know what? Why should we only take, okay, one more thing, I forgot. The default, or in most cases, gamma value is usually set as 0.9. Interview question. Gamma value in most cases is set at 0.9. Okay. If you apply gamma value as 0, that means you are going to use your basic gradient descent algorithm. There is nothing called momentum that is being applied. Because momentum value into gamma value if you choose as 0, this entire value becomes 0. So nothing from previous step is taken. Nothing from previous step is added to the current step. When you set gamma value equal to 1, the complete previous step change is being applied to the current step. That is when gamma equal to 1. But then, okay, one more thing is, this gamma value is called as a hyperparameter. Gamma value is called as hyperparameter. Then we have Nestor Momentum. When it comes to Nestor Momentum, there was a guy by name Nestor. Against that scientist's name, they gave this name as Nestor. So what Nestor says is, do you know what? If there is a momentum which is given, then again bouncing around the ball problem might arise. That is, you're taking some amount of the previous step and applying that to this step. So you might go and land there. Then you're taking some amount of this previous step and applying it to this step. So you might go there because there might be some additional momentum. This additional momentum might push you away from the minimum. Hence, what Nestor thought is, let us do one thing. Let us not just take the, if you're here, if you want to move to the next step, don't just take the past information to train, but let us also look at, if I take the past information and add it to this point, where will it go? Take this future information also. Don't just take the past information, take the future information also. And if you're going to be too far in the future, then adjust the value. So it's in some sense predicting where you land if I give you the momentum, and then reducing the value, momentum value, so that you don't go very far into the future. That is what Nestor Momentum does. Okay, very simple. And then you adjust. You adjust and ensure that you do not land very, very far in the future. Okay. Now let us understand certain things. Theory is fine at a high level, right? Now let me get into, the moment you use Nestor Momentum, this is what happens. It won't go very far. Right? This is what. But then how does it work? At a high level, there are 4 steps. Let me explain that. Step number 1 is, say you are at point B. This is point A. Now, as with gradient descent with momentum, when we are at point B, you look back at point A to find the change we computed at this step. How much was the gradient change? Let that be called as M, momentum. And then we scale it by a factor of gamma, momentum scaling factor. We add this scaled momentum to B to give it a new prediction point. Say the new point is somewhere going to be here. Let me call this as P. If you add the previous step momentum scaled by a scaling factor to this B, say you land here. Now we find the gradient at P, we are going to call it as G. And we are going to scale it by a learning rate, neta value. Say the gradient or rate of change at P will be G, and then you scale it by eta value. Then at point B, we add the scaled gradient at point P and the scaled momentum, this part, to give us a new point which will be C, somewhere here. Otherwise, you would have landed at P. At P, you are again looking at what will be the gradient. Usually, if you're at P, right, if you're this side, the next change at P will be coming backwards. So that change amount is G, scale it by eta, take this value and this value, add it to B, so it will land up there. Excellent. This is called as Nestor Momentum. So you have momentum, which will help you get out of flat plateaus and wherever you have shallow places, not deep, shallow places. Shallow means this is deep, this is shallow. If you are at shallow, it will help you get out of that. Okay, it has an additional benefit, that is, it will zip down steep slopes faster. Even with a small learning rate, when you have steep surfaces, it will come down faster. So your learning will be fast. And anytime we try out momentum, there is no harm in trying out Nestor Momentum, because Nestor Momentum does not have any additional parameter. For momentum alone, there is gamma, but for Nestor Momentum, there is no additional parameter that you need. So you can learn quickly with less noise. Deep learning is like, if you know deep learning, right? And when people ask you interview questions, you can take them in your direction. You can actually implement all these in your project. And when you talk to the interviewer, when you talk about momentum, Nestor Momentum, etc., they'll certainly get jolted that this guy is not like the regular people who speak only at a superficial level. This guy actually knows many things beyond that. So that is the kind of impression that you give. Okay. So this is a quick comparison between mini batch SGD with momentum, mini batch SGD with Nestor Momentum. If you look at this, to reach the minimum error, it took almost 5,000 epochs when people use mini batch SGD. But when you use mini batch SGD with momentum, in around 600 epochs, you could reach the minima. When you use Nestor Momentum, in approximately 400 epochs, you could reach. That's a huge improvement. So you can train your model very fast if you use Nestor Momentum. Okay, now in both momentum and Nestor Momentum, there is an eta value, learning rate value, that has to be chosen. Okay. But the same learning rate value, is used to update all weights. To update all weights, the same learning rate value is used. But then, can I have different learning rates for different weights? Or can I have tailored formula for different weights? So you have, if you have an algorithm, neural network like this, okay, then for all these weights, you will have the same formula. But can I have different weights or different formula for each of these weights? Can it be that adaptive? Can the learning rate be tailored for each and every weight? Is that a possibility? Yes. And when people experimented in that way, it started giving even better results. And one such thing, people started using something called as ADA, ADA grad, ADA delta, ADAM. All these mean adaptive. So you are going to adapt your weight updation, and you're going to change each and every weight using a different formula. I mean, different values for the formula. And ADA-grad is what we'll talk about. ADA-grad stands for, okay, let me explain. So ADA-grad stands for Adaptive Gradient Learning. As the name itself implies, right? ADA means change. Okay? Adaptive means change. And it is going to change the gradient of each weight. So change the gradient of each weight. Okay, changing the gradient of each weight is called as ADA-grad. ADA-grad is a way of performing learning rate decay. We already spoke about shrinking learning rate or learning rate decay parameter, exponential, delayed exponential, step, bull driver, all these are decay parameters. But here we are going to apply decay parameter on weight by weight basis. We are going to do it on weight by weight basis. So what you do is ideally, for every weight, again, say this is a kind of network that you have. You will have weights. Okay, all these are weights. Weight 1, weight 2, weight 3, weight 4, weight 5, weight 6, weight 7, weight 8. All these are weights, right? So for each weight that you're going to have, what ADA-grad does is, it will take the gradient we use in that step. Okay, it will take the gradient. Gradient can be denoted using this symbol. Gradient. Okay, you take the gradient at that stage. That means rate of change at that step. For every weight, take the gradient that you use in that step and then square that gradient. Multiply it with 7. Square it. And add it to the running sum. Meaning, if this is a gradient at step 1, then you'll have gradient at step 2 also. Then what you do is, you here at this step, take this also and update and add it. So you add the gradients. At step 3 also you'll have a gradient. You square it. But at this step, you maintain a running sum of all the gradients. Okay, you maintain the gradients. Add it to maintain the running sum. Running sum. Then take the gradient. Say you're at this step or at this step. Take that gradient and divide it by the value which is derived from this summation. At this step, it will be delta 3 divided by delta 1 square plus delta 2 square plus, sorry, gradient 3 square. Okay, and at this step, it will be this divided by, at this step, it will be divided by this running sum. At this step, it will be divided by the running sum in that. Now, and this value or this value or this value is ultimately used to update the weight. That is used to update. Because each gradient is squared, before it is added to the running sum, the value when you square becomes positive. Okay, and if you are adding it throughout, it will give a larger and larger value over time. And since these values are going to become larger and larger and larger, if you divide your gradients by those larger values, your ultimate weights become smaller and smaller over a period of time. The weight updations become smaller, 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 and they keep becoming smaller and smaller over a period of time. And as the time goes, the changes to the weights become smaller, 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 and very small. Okay, next. This is the one thing that you need to remember. But very often, just to kick off the process, here also you need to choose some learning rate, initial learning rate. You set that initial learning rate as usually 0.01, and you then leave it to your ADA grad. And then ADA grad is going to keep adjusting those values. Okay, next. Now, because the summation of these gradients become larger and larger over a period of time, and eventually you are dividing each gradient by that running sum, slowly the weight value will come to 0. And this is the reason why, if you look at your ADA grad here, after maybe 8,000 epochs, it is hitting the minimum loss or error. It's taking far too many epochs to reach the minimum. To solve this, we can use something called as ADA delta. And this ADA delta is very, very similar. This is nothing but adaptive once again. Adaptive delta means change. This ADA delta is very, very similar to something called as RMS prop. So we will discuss one, the other thing will follow. RMS prop stands for root mean squared propagated. Root mean squared propagated. Now, what happens here is something very interesting. So let's understand. So now we are talking about ADA delta or RMS prop. The problem with ADA grad is that we apply to each weight a number which gets smaller and smaller over a period of time. Okay. Now, what happens in ADA delta is you maintain the running list of the most recent gradients. So, if you maintain the gradient at step 1, gradient at step 2, gradient at step 3, gradient at step 4, gradient at step 5, gradient means the rate of change, right? And you square it, square the gradients. And in ADA grad, what were we doing? For this, delta 1 by delta 1, grad 1 by grad 1 square. For this step, it was grad 2 by grad 1 square plus grad 2 square. At this step, it is grad 3 divided by grad 1 square plus grad 2 square plus grad 3 square. At this step, it was grad 4 divided by grad 1 square plus grad 2 square plus grad 3 square, etc. Plus grad 4 square. So using everything right from the beginning, all these squared values will be used eventually. And then you get this new update, new weight. Here in ADA delta, what you do is you maintain all this, you maintain all these grad and square of it. Then you assign it position values. Grad 1 is the first position. Grad 2 is the second position. Grad 3 is the third position, so on and so forth. Then what you do is we add up the values in the list. Whatever is the grad, you multiply it with 1. Whatever is the grad, you multiply it with 2. Whatever is the grad, you multiply it with 3. So what will happen if you have something in the 100 position, you are multiplying it with 100. So that way, you are giving more weightage to the most recent grads, right? So the recent values are getting multiplied by a larger value. And the old ones are getting multiplied by small values, by 1, by 2, by 3, etc. So this way, our running sum that we are going to maintain, the running sum, will be heavily determined by the recent gradients. And it will be having less influence from the older ones. So the running sum of the gradients might increase or decrease based on the gradients we have applied most recently. This is called as ADA delta. So it adaptively changes how much weights are updated on each step using the weighted running sum. Okay. So this is how it works. So because of this very reason, because the learning rate, ADA delta adjusts the learning rates on the weights individually, certain times, certain weights can take you to a steep slope or it can slow down. Here also, initially to get started, the learning rate value is chosen at in most cases 0.01, and then leave it to the algorithm to adapt, to adjust. And as opposed to reaching the minimum error after 8,000 epochs, ADA-grad has taken 8,000 epochs. Here, ADA delta is reaching the same minimum in 2,000 epochs. But here, there is additional parameter in ADA delta that you have to choose. Like your momentum, here also there is a parameter called as gamma value. This value will tell us how much we need to scale down the gradients in the history. You will have all the gradients maintained, right? Gradient 1, gradient 2, gradient 3, gradient 4. How much we need to scale down the gradients in our history over a period of time, that is given by gamma. So gamma will remember values further back in history than small values, and it will add to the summation. Anyways, the gamma value is usually set at 0.9. Okay, so these are the interview questions. What is additional parameter? Gamma. And in ADA delta, there is yet another parameter called as epsilon. Right? It's called as epsilon. These are used to just ensure that the calculations are numerically stable. And most libraries will set this to a default value. And usually we don't change it. Right? Unless you are super expert at all these things, you don't change it. Okay. Same is the case with RMS prop. It has this gamma value, which is set at 0.9. Rest all remains the same. I would continue for just a few minutes because there is Adam, which is the third one, which is very, very similar in nature to ADA grad or ADA delta. So we have something called as Adam. Here, in these two algorithms, basically, what were we doing? We were taking the grad or gradient, and then we were squaring the gradient and we were storing it. Okay, and we maintain a running sum. If you have ADA delta, you also scale it down by gamma y. The old ones gets lesser weightage. The most recent gradients are more weightage. And at each gradient step, you divide it by the total running sum. So here you have grad 3 square, grad 4 square, and running sum was also maintained, grad 1 by grad 1 square. Here it is grad 2 by grad 1 square plus grad 2 square. Then here we have grad 3 by grad 1 square plus grad 2 square plus grad 3 square. Grad 4 by grad 1 square plus grad 2 square plus grad 3 square plus grad 2 square. In this way, we used to maintain, right? But here, since we are squaring, we are giving importance only to the positive values. And in ADA grad, we were giving equal weightage to all of these. But in ADA delta or RMS prop, we were treating older elements as less important and the newer gradients with more importance. Squaring the gradient before putting it into this, calculation, into these calculations, always result in positive values. This means we are tracking only positive values. That's useful information to have. But we are losing the track of negative values. So negative values also should be maintained. Whether we have positive or negative gradients is important. Are you coming down or going up? All those things are important. So what Adam does is, it will maintain one list of gradients as is, and it will maintain another list by squaring them. Then both of these, the ones which are not squared and the ones which are squared, both of them are used in arriving at that scaling factor. And this approach is called as adaptive moment estimation. Adaptive moment estimation. Okay, now here, if you look at it, there is slight noise, right? But that's okay. Ultimately, here, what is happening is, if you look at this ADA grad, after 8,000 epochs, you are reaching the minima. Here, after 2,000 epochs, here, after 1,000 epochs, so fast. But the only disadvantage with gamma is that it will have two parameters, beta 1, beta 2. Okay. Beta 1 has a value, default value of 0.9. The authors who came up with this algorithm say that they have used 0.9 for beta 1 and for beta 2 they have used 0.999. And these values work extremely well in almost all the settings. Okay. So when people experimented with mini batch SGD with Nestor Momentum, ADA grad, ADA delta, Adam, which one will work well? We don't know, but usually Adam works well. But in this scenario, in this experiment which some author has done, mini batch SGD with Nestor was helping reach the minimum error surface in less number of epochs, faster. Okay, very fast, it helps you achieve. But remember one thing, friends, there is no free lunch theorem. If you ask me, out of all these optimizers, why can't you name just one which works exceptionally well? I cannot, unfortunately. So there is no free lunch. You have to work hard. Okay. So here are a few standard options which people use. SGD plus Nestor Momentum. Usually SGD means mini batch SGD. Or mini batch SGD with AdaGrad or RMS Prop or Adam. If you're really pressed for time, try out Adam. It works well in most cases. Then when it comes to using the neurons in the hidden layer, using the activation functions in the hidden layers, Rayleigh or Leaky Rayleigh or max out are giving best results. So you can try out those. But output, you know what neurons you have to use. We already have spent time here. If you have an output variable continuous, use this activation function in the output. If you have discrete with two categories, use this. If you have discrete with more than two categories, use something else. We already discussed about this. So these are the various things, and I've been doing a recap, so not to worry. And please ensure that you read this mind map thoroughly. Okay, and here in the mind map, all the various details are clearly mentioned. Okay, we'll keep updating this. We'll keep adding new things to this, such as what are the default hyperparameters, what are the default learning rate values which people usually give. Those kind of things we'll update. But then remember that this is going to be your ready reckoner to review everything. Okay. All right, I'll stop here. Thank you so much for attending. And